Tonight, we are going to sit with one of the more quietly destabilizing scientific situations in modern cosmology. For about 3 decades, the textbook number for the age of the universe has been 13.8 billion years, derived primarily from the cosmic microwave background measurements of the Planck satellite. The number has been treated as essentially settled. It appears in every introductory astronomy textbook. It shows up in every popular cosmology article. It is one of the more confident statements that modern science has been able to make about the deep structure of physical reality. Over the past 3 years, the James Webb Space Telescope has been quietly returning observations that, in several specific ways, do not fit comfortably with this number. The data is not casual. The observations are not single tentative detections. The pattern across multiple independent surveys is consistent. The galaxies appearing in the very early universe at cosmic times less than 400 million years after the Big Bang are larger and more chemically developed and more structurally mature than the standard timeline allows. Stars in our own galaxy have been observed to have ages that, by some measurements, exceed the cosmic age itself. The local measurement of the cosmic expansion rate continues to disagree with the cosmic microwave background measurement by an amount that has not been satisfactorily explained. Tonight, we're going to walk through 5 specific observations that, taken together, suggest the cosmic age may need to be revised upward. The work is not yet definitive. The mainstream interpretation of the observations is still that the galaxy formation models need refinement rather than that the cosmic age needs revision. But the data is consistent enough across multiple independent lines of evidence that the alternative interpretation that the universe is actually older than the standard 13.8 billion year value has begun to receive serious published attention. Tonight, we are going to walk through the evidence for both interpretations and look at what the actual current state of cosmological understanding is. Before we get started, sit with what is at stake. The age of the universe is one of the most fundamental parameters in cosmology. It enters into essentially every calculation about cosmic structure, every prediction about cosmic future, every interpretation of cosmic observations. A revision to the cosmic age, if it turns out to be required by the new data, would propagate through essentially every aspect of modern cosmology. The implications would extend across multiple research areas, with substantial work being required to rederive the various standard results within the modified framework. Tonight, we're going to walk through 5 specific reasons that the cosmic age may need to be revised. Each one is a real empirical observation. Each one has implications for the broader picture of cosmic history. Each one helps explain why a small but growing minority of serious cosmologists has begun to take the alternative cosmic age interpretations seriously. The 5 reasons are these. The first reason is that the James Webb Space Telescope has detected galaxies at very high redshifts that appear too massive, too bright, and too chemically enriched to have formed within the standard cosmic timeline. The most distant confirmed galaxy, JWST 14-0, is observed at a redshift of approximately 14.3. corresponding to a cosmic time of about 290 million years after the Big Bang. The galaxy contains approximately 400 million solar masses of stars, with metallicities indicating that substantial chemical evolution has already occurred. The standard galaxy formation models predict galaxies at this cosmic time should be much smaller and much less developed than what is observed. The second reason is that specific stars within our own galaxy, called Methuselah stars, have measured ages that, by some analyses, exceed the cosmic age itself. The most famous example is HD 140,283, a metal-poor star in the constellation Libra, whose age has been estimated at approximately 14.5 billion years with substantial uncertainty. The mean estimate is older than the standard cosmic age, with the uncertainty range overlapping with the standard cosmic age value. The situation is not impossible but is uncomfortable, and various analyses have been performed to try to bring the stellar age estimates into more comfortable agreement with the standard cosmic age. The third reason is the persistent Hubble tension between local measurements of the cosmic expansion rate and the cosmic microwave background measurements. The local measurements, based on the cosmic distance ladder using Cepheid variable stars and type A supernovae, give a Hubble constant of approximately 73 kilometers per second per megaparsec. The cosmic microwave background measurements based on the Planck satellite combined with the standard cosmological model give a Hubble constant of approximately 67 kilometers per second per megaparsec. The disagreement has been around for a decade and has not been satisfactorily explained. Various proposed explanations involve new physics that would also affect the cosmic age estimate. The fourth reason is that supermassive black holes have been observed at cosmic times less than 700 million years after the Big Bang, with masses that are difficult to explain through the standard formation mechanisms within the available cosmic time. The galaxy GNZ11, observed at a redshift of approximately 10.6, contains a supermassive black hole of approximately 1 to 2 million solar masses. The standard accretion mechanisms cannot grow a black hole from a stellar mass seed to this size within the available cosmic time, without invoking either super-Eddington accretion or direct collapse seed mechanisms that are themselves not fully understood. The fifth reason is that alternative cosmological models have been published that propose substantially older cosmic ages while remaining consistent with most of the available observational data. The most prominent recent example is the work of Rajendra Gupta at the University of Ottawa, who proposed in 2023 a modified cosmological model that incorporates tired light and varying coupling constants. The Gupta model gives a cosmic age of approximately 26.7 billion years, almost twice the standard value. The model has been published in mainstream journals and has received serious attention from some cosmologists, though it remains a minority view in the broader cosmology community. 5 reasons. 5 specific, empirical and theoretical considerations that, taken together, raise serious questions about whether the standard 13.8 billion-year cosmic age value is fully correct. By the end of tonight, you will have walked through each one slowly, with enough detail to understand both the strength and the limitations of the various arguments. Pattern interrupt. The tone of tonight should not be claim that the cosmic age has been definitively revised. The mainstream cosmology community still treats the 13.8 billion year value as the best current estimate, with the various tensions being attributed to specific limitations of current models or to specific systematic uncertainties in the measurements. The alternative interpretations that we will walk through tonight are minority views within the broader cosmology community. But the minority views are not crackpot. They are published in mainstream journals. They are taken seriously by some careful cosmologists. The work continues. Now, let's begin with the first reason. The James Webb galaxies that appear too developed for their cosmic age. Before we get started, sit with what follows. The basic situation is this. The James Webb Space Telescope was designed specifically to observe the very early universe, taking advantage of its infrared sensitivity to detect the redshifted light from galaxies at very high redshifts. The telescope was launched in December of 2021 and began full science operations in mid-2022. Within months of beginning science operations, the telescope began returning observations that did not fit the standard expectations for galaxies at the cosmic epochs being observed. The standard expectations were derived from decades of theoretical work on galaxy formation, combined with the observations from earlier telescopes, including the Hubble Space Telescope. The expected pattern was that galaxies at very high redshifts should be small, faint, and structurally immature, having had limited cosmic time to accumulate stars and develop the structural features of mature galaxies. The standard predictions prior to the James Webb observations suggested that galaxies at redshifts above 10 should be detectable, but should be substantially smaller than the galaxies observed at the lower redshifts where Hubble had been operating. By the end of tonight, you're going to understand that the James Webb observations have substantially overturned these expectations. The galaxies observed at redshifts above 10 are systematically larger and brighter than the standard predictions allowed. The mass functions, luminosity functions, and chemical enrichment levels are all shifted toward higher values than the standard models predict. The pattern is consistent across multiple independent surveys, with the JD's survey, the SEERS survey, the Cosmos Web survey, and various other programs all reporting similar findings. Pattern interrupt. The specific case that has received the most attention is JWST 14-0. The galaxy was identified as a high redshift candidate in JD's imaging data and was confirmed at a redshift of 14.3 through detailed NIR spectroscopy, published in 2024. The spectrum showed clear emission lines from oxygen, nitrogen, and carbon, indicating substantial chemical enrichment by previous stellar generations. The stellar mass of the galaxy, estimated from the spectrum and the photometry, is approximately 400 million solar masses. The implications for the cosmic timeline are direct. At a cosmic time of approximately 290 million years after the Big Bang, the standard models predicted that galaxies should have stellar masses of perhaps a few million solar masses at most, with chemical enrichment essentially non-existent. The observed galaxy exceeds these predictions by factors of 50 to 100 in stellar mass, and by similar factors in chemical enrichment. The galaxy is, by every available measurement, much more developed than the standard timeline allows for its cosmic age. The mainstream interpretation of this observation is that the standard galaxy formation models need refinement rather than that the cosmic age itself needs revision. The proposed refinements include various adjustments to the initial mass function of the first stars, to the star formation efficiency in the early universe, to the feedback processes that regulate star formation, and to various other aspects of the standard models. The refinements can, in principle, accommodate the observed galaxy properties without requiring fundamental changes to the cosmic age. By the end of tonight, you're going to understand that this mainstream interpretation has both strengths and limitations. The strength is that the proposed refinements are consistent with the existing data and do not require fundamental changes to the broader cosmological framework. The limitation is that the refinements have not been independently confirmed, and that the specific physical mechanisms required to produce the observed early galaxy properties are not fully understood. The alternative interpretation, that the cosmic age may need to be revised upward, has been advanced by various researchers. If the cosmic age is older than the standard 13.8 billion year value, then the cosmic time available for galaxy formation at any given redshift is greater than the standard calculations suggest. The galaxies observed at high redshifts would have had more time to develop than the standard timeline allows, with the observed properties being more easily accommodated within the modified framework. No one expects, on first encountering modern cosmology, that the careful James Webb observations of distant galaxies would have implications for the most fundamental cosmological parameter of all, namely, the age of the universe. No one predicts that the observed galaxy properties at high redshift would lead to serious discussion of cosmic age revision. Absolutely no one anticipates the way the empirical study of the cosmic dawn era has become so directly connected to questions about the foundational cosmological parameters. Walk with me through one specific empirical implication. The number density of bright galaxies at very high redshifts has been measured systematically through multiple James Webb surveys. The measured number densities consistently exceed the standard predictions by factors of 2 to 5, depending on the specific redshift range and the specific brightness threshold. The excess is statistically significant and is observed across multiple independent surveys. The excess number density implies that either the galaxy formation efficiency is substantially higher than the standard models assume, or that the cosmic time available for galaxy formation is substantially longer than the standard timeline allows. Both interpretations are consistent with the observed data, with the distinction between them depending on whether other cosmological measurements can independently constrain the cosmic age. Tonight, we're going to spend a longer pass on the specific JWST 14-0 observations, because the galaxy is the most distant confirmed galaxy ever observed, and the details deserve careful examination. The galaxy was identified as a high redshift candidate in JWST photometric data taken during the first year of James Webb operations. The JD's survey, the JWST Advanced Deep Extragalactic Survey, was specifically designed to identify and characterize galaxies at the highest possible redshifts. The survey uses multiple James Webb instruments operating in coordination, with the NIR-CAM instrument providing wide-field photometric imaging and the NIR-SPEC instrument providing detailed spectroscopy of the most promising candidates. The photometric identification of JWST 14-0 was based on its specific colors in the various NIR-CAM filters. Galaxies at very high redshifts have their light substantially shifted toward longer wavelengths by the cosmic expansion. The shifting moves specific spectral features into specific wavelength ranges, with the resulting color patterns being distinctive enough to identify the high redshift candidates from the much more numerous lower redshift galaxies in the survey area. By the end of tonight, you're going to understand that the specific identification process involves several stages. The first stage uses the near-cam photometry to identify candidates whose colors are consistent with high redshift galaxies. The candidates are then evaluated against various potential sources of contamination, including foreground galaxies whose colors might mimic the high redshift signature. The most promising candidates are then targeted for spectroscopic follow-up with NIR-SPEC, which can definitively determine the redshift by measuring specific spectral lines, pattern interrupt. The NIR-SPEC spectroscopy of JWST 14-0 was performed in 2024. The spectroscopic observations revealed clear emission lines from oxygen, nitrogen, and carbon at specific wavelengths that, when interpreted as redshifted versions of the standard emission lines for these elements, gave a redshift of approximately 14.3. The redshift corresponds to a cosmic time of approximately 290 million years after the Big Bang, making the galaxy the most distant confirmed galaxy ever observed at the time of the publication. The detailed analysis of the spectrum has provided substantial information about the galaxy's properties. The stellar mass derived from the total brightness combined with the spectrum shape is approximately 400 million solar masses. The star formation rate derived from the strengths of specific emission lines is approximately 5 solar masses per year. The metallicity derived from the ratios of various emission lines is approximately 1/10 of solar. The implications of these measurements are substantial. At a cosmic time of approximately 290 million years after the Big Bang, the standard galaxy formation models predicted galaxies should have stellar masses of perhaps a few million solar masses at most, with star formation rates of perhaps 0.1 solar masses per year, with metallicities essentially zero. The observed JWST 14-0 exceeds all of these predictions by factors of 100 to 1000. The galaxy is, by every available measurement, substantially more developed than the standard timeline allows. By the end of tonight, you're going to understand that the JWST 14-0 observations are not isolated. Several other galaxies at similar redshifts have been confirmed by various James Webb surveys, with each one showing similar patterns of being more developed than the standard timeline allows. The Sears survey, the Cosmos Webb survey, and various other programs have all reported similar findings. The pattern is consistent across multiple independent surveys. The specific spectroscopic measurements include detailed information about the gas conditions in the galaxy. The relative strengths of the oxygen emission lines provide constraints on the gas temperature and density. The presence of nitrogen emission lines provides constraints on the nitrogen abundance, which is one of the more unusual features of the galaxy. The nitrogen-to-oxygen ratio in JWST 14-0 is substantially higher than the ratios observed in modern galaxies at similar metallicities, suggesting that specific nucleosynthetic processes have operated in the galaxy that are not common in the modern cosmos. Walk with me through one specific implication. The high nitrogen abundance has been interpreted as evidence for specific stellar populations that produce nitrogen through specific nuclear processes. The most likely candidates are very massive stars in the range of hundreds of solar masses, which can produce nitrogen through specific nucleosynthetic channels in their late evolution. The presence of such stars at the cosmic time when JWST 14-0 is observed implies that the very first stellar generations had already evolved through their lifetimes by the time of the observation. The implications for the cosmic timeline are direct. The first population 3 stars are estimated to have formed approximately 100 to 200 million years after the Big Bang. The lifetimes of very massive stars are approximately a few million years. The cosmic time required for the first stars to form, live and die would be approximately 100 million to 210 million years. The observed JWST 14-0 is at a cosmic time of approximately 290 million years. The cosmic time between the death of the first massive stars and the observation of JWST 14-0 would be approximately 80 to 190 million years. The time available for the chemical enrichment from the first stellar generations to be incorporated into the galaxy for additional stars to form from the enriched gas and for the galaxy to assemble to its observed mass and properties is approximately 100 million years or less. The standard galaxy formation models suggest that this cosmic time is at the edge of what is theoretically possible, even with optimistic assumptions about the star formation efficiency and the chemical mixing rates. No one expects, on first thinking about galaxy formation, that the empirical observations of distant galaxies would push the standard timeline to such an empirical edge. No one predicts that a single, specific galaxy would have such substantial implications for the broader cosmic age question. Absolutely no one anticipates the way that JD's GSZ 14-0 observations have substantially advanced the empirical case for the various open cosmological questions we are walking through tonight. The follow-up observations of JD's GSZ 14-0 are continuing. Additional James Webb spectroscopy is expected to refine the various property measurements. ALMA submillimeter observations are expected to detect the dust thermal emission from the galaxy, providing additional constraints on the dust content. The combined observational program will, over the coming years, substantially improve our characterization of this specific galaxy and its implications for the broader cosmological framework. Pattern interrupt. The implications extend beyond just the specific case of JD's GSZ 14-0. The galaxy is one of several similar objects at the highest confirmed redshifts. The cumulative empirical picture is that galaxies at the cosmic dawn era are systematically more developed than the standard timeline allows. The pattern is consistent enough across multiple independent observations that the implication for the broader cosmological framework is substantial. Hold this image. JD's GSZ 14-0 is a specific galaxy observed at a redshift of approximately 14.3, corresponding to a cosmic time of about 290 million years after the Big Bang. The galaxy contains approximately 400 million solar masses of stars, with substantial chemical enrichment indicating that previous stellar generations have already operated. The galaxy's properties exceed the standard timeline predictions by factors of 100 to 1000 in various specific measurements. The empirical case for the broader cosmological revisions we are walking through tonight is substantially advanced by this specific observation. Hold this image. The James Webb observations of high redshift galaxies have substantially complicated the standard cosmological picture. The galaxies observed at the highest redshifts are systematically larger, brighter, and more chemically enriched than the standard timeline allows. The mainstream interpretation involves refinements to the galaxy formation models. The alternative interpretation involves revision to the cosmic age. The empirical question of which interpretation is correct is still being investigated, with substantial work expected over the coming years as additional James Webb data accumulates. The second reason the cosmic age may need revision is one of the more remarkable empirical findings in modern stellar astronomy. There are stars in our own galaxy whose measured ages, by some analyses, exceed the standard cosmic age itself. Tonight, we're going to walk into the specific case of HD 140,283, called the Methuselah star, because this single object encapsulates much of what is empirically uncomfortable about the standard cosmic age. The basic situation is this. The age of a star can be measured through several different methods. The most reliable method involves fitting the star's observed properties, including its temperature, luminosity, and surface gravity, to detailed stellar evolution models. The models calculate how stars of different masses evolve over their lifetimes with the observed properties at any given age depending on the specific stellar mass and the specific composition. By matching the observed properties to the model predictions, the stellar age can be derived with some precision. HD 140,283 was first identified as a particularly old star in the 1950s. The star is metal poor with iron abundance approximately 1/10,000th of the solar value. The low metallicity indicates that the star formed from gas that had been only minimally enriched by previous generations of stellar nucleosynthesis. The star must have formed in the very early universe, shortly after the first generations of stars had begun to scatter their nucleosynthetic products into the surrounding gas. By the end of tonight, you're going to understand that the specific age of HD 140.0283 has been the subject of substantial work over the past several decades. The most influential modern analysis was performed by Howard Bond at the Pennsylvania State University and his collaborators, with the results published in 2013. The Bond analysis used the latest available stellar evolution models combined with precise distance measurements from the Hubble Space Telescope to derive a stellar age of approximately 14.5 billion years with a 1 sigma uncertainty of approximately 800 million years. Pattern interrupt. The implications of this measurement are direct. The standard cosmic age is 13.8 billion years. The Bond age estimate of HD 140.0283 is 14.5 billion years. The difference is 700 million years, which is comparable to the uncertainty in the stellar age estimate. The stellar age taken at face value exceeds the cosmic age by an amount that is at the boundary of statistical significance. The situation is not strictly impossible within the standard cosmological framework, but it is genuinely uncomfortable. The subsequent work has refined the picture somewhat. Various refinements to the stellar evolution models, to the assumed oxygen abundance, and to the distance measurements have brought the central age estimate down to approximately 14.3 billion years in some analyses. The refinements bring the stellar age into closer agreement with the cosmic age, but they do not fully resolve the tension. The mean stellar age remains slightly older than the standard cosmic age, with the uncertainty range continuing to overlap with values that exceed the cosmic age. By the end of tonight, you're going to understand that HD 140.0283 is not the only star in this situation. Several other Methuselah stars have been identified, each with measured ages that approach or exceed the standard cosmic age. The Andromeda Galaxy contains analogous stars that have been studied through orbital observations. The Magellanic Clouds contain similar objects. The cumulative empirical picture is that there exists a population of very old stars whose ages are difficult to reconcile with the standard cosmic age within reasonable statistical confidence. The mainstream interpretation of this empirical situation is that the stellar age estimates contain larger systematic uncertainties than the formal uncertainty ranges suggest. The proposed sources of systematic uncertainty include various aspects of the stellar evolution models, including the treatment of mixing processes, the treatment of nuclear reaction rates at low energies, and the treatment of helium abundance in the early universe. The systematic uncertainties, when properly accounted for, may bring the stellar ages into more comfortable agreement with the standard cosmic age. Walk with me through one specific theoretical adjustment. The helium abundance in the very early universe affects the lifetime of low-mass stars in specific ways. The standard Big Bang nucleosynthesis predicts a helium abundance of approximately 24% by mass at the moment of the first star formation. If the actual helium abundance was slightly higher or slightly lower than this value, the stellar lifetimes would be modified, with implications for the derived stellar ages. The various analyses have explored different assumptions about the early universe helium abundance, with the derived stellar ages depending sensitively on the specific assumptions. By the end of tonight, you're going to understand that the empirical question of the actual stellar ages is not fully resolved. The various analyses produce somewhat different results depending on the specific assumptions used. The mean stellar age estimates for HD 140, 02, 83, and similar stars are systematically close to or slightly above the standard cosmic age. The systematic uncertainty range allows for stellar ages that are comfortably within the standard cosmic age, but the central estimates suggest a tension that has not been fully resolved. The alternative interpretation that the cosmic age may need to be revised upward would more comfortably accommodate the observed stellar ages. If the cosmic age is approximately 15 billion years rather than 13.8 billion years, the Methuselah stars would have ages substantially below the cosmic age, with no tension between the two measurements. The alternative interpretation is consistent with the stellar age data without requiring the systematic uncertainty adjustments that the mainstream interpretation invokes. No one expects, on first thinking about stellar evolution, that the careful study of single stars in the solar neighborhood would have implications for the most fundamental cosmological parameters. No one predicts that the empirical age estimates of specific stars would come close to challenging the cosmic age itself. Absolutely no one anticipates the way the Methuselah star phenomenon has become one of the more empirically uncomfortable situations in modern cosmology. No one expects these broader implications to be so direct, but they are. The implications for the broader picture of cosmic dating are substantial. The standard cosmic age is derived primarily from the cosmic microwave background measurements combined with the standard cosmological model. The cosmic age is one of the more confident determinations that modern cosmology has been able to make. The empirical observation of stars whose ages approach or exceed the cosmic age suggests either that the stellar age estimators contain larger systematic uncertainties than acknowledged, or that the cosmic age estimate itself contains larger uncertainties than acknowledged. The situation has not been fully resolved. Pattern interrupt. The work on Methuselah stars continues. The Gaia satellite, operated by the European Space Agency since 2013, has provided substantially improved distance measurements for many old stars in the solar neighborhood. The improved distance measurements allow more precise derivations of the stellar properties and therefore of the stellar ages. The various analyses incorporating Gaia data are progressively refining the Methuselah star age estimates, with the results substantially advancing our understanding of the empirical situation. By the end of tonight, you're going to understand that this is part of why the Methuselah star phenomenon is empirically valuable. The phenomenon is not just a curiosity, it is a direct, empirical probe of the consistency between the stellar evolution framework and the cosmological framework. The two frameworks must produce consistent results for the same physical reality, and any tensions between them indicate that further work is needed in one or both frameworks. Hold this image HD 140,283 is a specific star in the constellation Libra, whose measured age, by various analyses, is uncomfortably close to or slightly above the standard cosmic age. No one predicts the empirical situation in advance. The empirical situation is not strictly impossible within the standard framework, but it is sufficiently uncomfortable that various adjustments to the analyses have been proposed to bring the stellar age more comfortably below the cosmic age. The alternative interpretation that the cosmic age may need to be revised upward would more directly accommodate the empirical data. The work continues. Before we walk into the third reason, take a slow breath here. Tonight, we're going to walk through the specific scientific history of HD 140,283 because the star's dating story is one of the more remarkable in modern stellar astronomy and provides essential context for understanding the broader Methuselah star phenomenon. The basic situation is this: HD 140.0283 is a star in the constellation Libra, visible to the naked eye from dark sites under good observing conditions. The star has been studied by astronomers since at least the late 19th century, when its spectrum was first recorded. The star was identified as unusually metal-poor in the early 20th century, with the metal content being substantially lower than the solar value. The low metallicity indicated that the star is genuinely old, having formed from gas that had been only minimally enriched by previous generations of stellar nucleosynthesis. The specific age of the star has been the subject of substantial work over the past several decades. The age estimates depend on the specific stellar evolution models used in the analysis, on the specific distance measurement used to derive the star's intrinsic properties, and on various other technical aspects of the calculation. Different analyses have produced different specific age estimates, with the variation being substantial. By the end of tonight, you're going to understand that the most influential modern analysis was performed by Howard Bond at the Pennsylvania State University and his collaborators, with the results published in 2013 in the Astrophysical Journal Letters. The Bond analysis used the latest available stellar evolution models from the Padova group and from the Basti group, combined with the precise distance measurement of the star from Hubble Space Telescope parallax observations. The combined analysis derived a stellar age of approximately 14.5 billion years. Pattern interrupt. The 1 sigma uncertainty in the Bond age estimate is approximately 800 million years. The standard cosmic age is 13.8 billion years. The Bond central age estimate exceeds the standard cosmic age by approximately 700 million years, which is comparable to the formal uncertainty. The stellar age, taken at face value, is older than the cosmic age by an amount that is at the boundary of statistical significance. The situation is not strictly impossible within the standard framework, but it is genuinely uncomfortable. The subsequent analyses have produced various refinements to the original Bond results. The most important refinements involve the specific treatment of the stellar oxygen abundance. The oxygen abundance is one of the more uncertain elements in metal-poor stars, with the various measurements producing somewhat different specific values. Different oxygen assumptions produce different specific age estimates, with higher oxygen abundances generally producing somewhat younger ages and lower abundances producing somewhat older ages. Analyses by various groups incorporating improved oxygen abundance measurements and improved stellar evolution models have brought the central age estimate for HD 140.0283 down somewhat, The current best estimates place the central age in the range of 14.3 to 14.5 billion years, with 1 sigma uncertainties of 7 to 900 million years. The current central estimates remain slightly older than the standard cosmic age, with the uncertainty ranges continuing to overlap with cosmic age values. By the end of tonight, you're going to understand that the empirical situation is not fully resolved. The various analyses produce somewhat different specific age estimates depending on the specific assumptions used. The central estimates are uncomfortably close to or slightly above the standard cosmic age. The systematic uncertainty range allows for stellar ages that are comfortably within the standard cosmic age, but the central estimates suggest a tension that has not been fully resolved through purely technical adjustments. Walk with me through one specific technical aspect. The age of a star like HD 1400283 is derived through a specific technique called subgent branch fitting. The subgent branch is the evolutionary stage that follows the main sequence, when the star has exhausted the hydrogen in its core and is transitioning to burning hydrogen in a shell around the core. The location of a star on the subgent branch depends sensitively on its age and its specific composition, allowing the age to be derived from the observed properties. The technique requires precise measurements of the star's temperature, luminosity, and metallicity. The temperature and luminosity are derived from the star's spectrum combined with the distance measurement. The metallicity is derived from the detailed analysis of specific spectral lines. The combination of these measurements, when fitted to the subgiant branch in stellar evolution models, gives the stellar age. The various sources of uncertainty in the age estimate include the uncertainty in the distance measurement, the uncertainty in the temperature and luminosity derivations, the uncertainty in the metallicity measurement, and the systematic uncertainty in the stellar evolution models themselves. Each of these sources has been progressively improved over the past several decades. The current state-of-the-art analyses incorporate the best available data for each of these aspects, but the residual uncertainty remains substantial. By the end of tonight, you're going to understand that the systematic uncertainty in the stellar evolution models is one of the more important sources of uncertainty in the age estimate. Different stellar evolution codes, when applied to the same observed star, can produce somewhat different age estimates. The differences are typically a few 100 million years, which is substantial compared to the precision of the comparison with the cosmic age. The various analyses have used different stellar evolution codes, with the resulting age estimates falling in a range that reflects the variation in the model predictions. The Methuselah star phenomenon is not unique to HD 1400283. Several other stars have been identified with similar age estimates that approach or exceed the standard cosmic age. The most prominent examples include several stars in the globular cluster Messier 92, which is one of the oldest globular clusters in the Milky Way halo. The cluster age has been estimated at approximately 13 to 14 billion years by various analyses, with similar systematic uncertainty issues to those affecting the HD 1400283 analysis. No one expects, on first thinking about stellar dating, that the empirical age estimates for specific old stars would approach or slightly exceed the cosmic age value. No one predicts that the careful analysis of single stars would have such direct implications for the broader cosmological framework. Absolutely no one anticipates the way the Methuselah star phenomenon has, despite its apparent specificity, become one of the more empirically uncomfortable situations in modern cosmology. Pattern Interrupt, the Gaia satellite mission, has provided substantially improved distance measurements for HD 140-0283 and for many other old stars in the solar neighborhood. The Gaia distance measurements are based on parallax, the same fundamental technique used by Hubble but with substantially improved precision. The improved distance measurements allow more precise derivations of the stellar properties and therefore more precise age estimates. The various Gaia-based analyses of HD 140-0283 have produced age estimates similar to the previous Hubble-based analyses, with central values in the range of 14.3 to 14.5 billion years. The Gaia results have therefore not fundamentally resolved the Methuselah star tension. The work continues with additional refinements expected as the Gaia mission continues to operate, and as the stellar evolution models continue to be refined. Hold this image. HD 140-0283 is a specific old star in the constellation Libra, whose measured age by various careful analyses approaches or slightly exceeds the standard cosmic age. The empirical situation is not strictly impossible within the standard cosmological framework, but it is sufficiently uncomfortable that various technical adjustments have been proposed to bring the stellar age more comfortably below the cosmic age. The work continues with the empirical question remaining genuinely open. Before we continue, why this channel exists. If you have made it this far into a careful examination of why the cosmic age may need revision, you are not the casual viewer the platform expects. You are the person for whom this channel was built. Long-form cosmology, told at the pace of sleep, with enough technical detail to actually feel the weight of the open questions rather than just the headline summaries, is not what the algorithm rewards. It is what we make anyway. Because we believe the cosmos is more interesting when the open questions are developed slowly rather than collapsed into viral fragments. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about reality. If you have already subscribed, thank you. Truly. If this is your first long-form night with the channel, welcome. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there. The audio versions are tuned for the same purpose, the same pace, the same care. Now, let us return to the data. The third reason is waiting. The third reason the cosmic age may need revision is the persistent Hubble tension between two different ways of measuring the cosmic expansion rate. Tonight, we're going to walk through this carefully because the Hubble tension is one of the most studied open problems in modern cosmology, and its implications for the cosmic age are direct. The basic situation is this. The cosmic expansion rate, called the Hubble constant in honor of Edwin Hubble, who first measured it in 1929, determines how fast distant galaxies are receding from us due to the cosmic expansion. The Hubble constant is conventionally expressed in units of kilometers per second per megaparsec. A galaxy at a distance of 1 megaparsec recedes from us at a velocity equal to the Hubble constant value. A galaxy at 10 megaparsecs recedes at 10 times that velocity. The basic relationship is the cornerstone of modern observational cosmology. The Hubble constant can be measured in two main ways. The first way is the local measurement, which uses nearby objects, whose distances can be measured directly through specific astronomical techniques. The most common local approach involves the cosmic distance ladder, which calibrates Cepheid variable stars against parallax measurements of nearby stars, and then calibrates Type Ei supernovae against the Cepheid distances. The Type Ia supernovae can be observed across substantial cosmic distances, allowing measurement of the Hubble flow at large redshifts. The combined local distance ladder produces a Hubble constant estimate. What emerges from this is that the local distance ladder measurement, performed most carefully by the SH0ES collaboration led by Adam Rees at Johns Hopkins, gives a Hubble constant of approximately 73 kilometers per second per megaparsec, with a quoted uncertainty of approximately 1%. The measurement has been progressively refined over the past 2 decades, with the central value being remarkably stable across multiple independent analyses by various research groups. The second way is the cosmic microwave background measurement, which uses the temperature variations in the cosmic microwave background combined with the standard cosmological model to derive the various cosmological parameters, including the Hubble constant. The most precise measurements come from the Planck satellite, operated by the European Space Agency between 2009 and 2013. The Planck measurements give a Hubble constant of approximately 67 kilometers per second per megaparsec, with a quoted uncertainty of approximately 1%. Pattern interrupt. The two measurements disagree by approximately 9%. Both measurements have quoted uncertainties of approximately 1%. The disagreement is therefore approximately 9 times the combined uncertainty, which is statistically very significant. The disagreement is not a small effect that might be attributed to systematic errors at the 1% level. The disagreement is a substantial discrepancy that requires explanation. The Hubble tension has been the subject of substantial work over the past decade. The proposed explanations fall into several broad categories. The first category invokes systematic errors in one of the measurements. Various aspects of the local distance ladder have been examined for possible systematic errors, including the calibration of Cepheid variables, the absolute distance scale derived from parallax measurements, and the standardization of type Ia supernovae. Various aspects of the cosmic microwave background analysis have similarly been examined. The systematic error investigations have not identified any specific issues that would explain the full magnitude of the tension. The second category invokes new physics that would modify the cosmic expansion history in ways that affect the two measurements differently. The proposals include time-varying dark energy, early dark energy, exotic interactions in the dark sector, modifications to general relativity at cosmic scales, and various other possibilities. Each of the proposals has been worked out in detail by various theoretical groups, with the resulting models being tested against the available cosmological data. What becomes clear is that the new physics proposals have substantial implications for the cosmic age. The standard cosmological model derives the cosmic age from the Hubble constant combined with the other cosmological parameters. A modified cosmological model that successfully resolves the Hubble tension would, in general, produce a different cosmic age than the standard model. The specific cosmic age depends on the specific modifications, with the various proposals producing different specific predictions. Walk with me through one specific example. The early dark energy proposal involves a brief period of accelerated cosmic expansion in the very early universe, before the cosmic microwave background was emitted. The accelerated expansion modifies the cosmic timeline in specific ways, with the implications for the cosmic age depending on the specific parameters of the early dark energy model. The cosmic age in the early dark energy framework is, in some specific implementations, somewhat younger than the standard cosmic age. In other implementations, the cosmic age is somewhat older. The framework, therefore, allows substantial flexibility in the cosmic age value. Other new physics proposals produce other implications. The varying dark energy proposals can produce cosmic ages substantially different from the standard value. The varying coupling constant proposals can produce different ages as well. The modified gravity proposals can produce different ages. The various proposals span a substantial range of possible cosmic age values, with the standard 13.8 billion year value being one specific outcome rather than a guaranteed result. The third category of explanations invokes the possibility that we live in an underdensity that biases the local measurements. If the local cosmic region has somewhat lower density than the cosmic average, the local expansion measurement would be biased upward relative to the global cosmic average. The underdensity explanation has been worked out in detail by various groups, including the work of Hao-Yi Wu and Dragan Hutera, and the work of Moritz Hasselbauer and Pavel Krupa. The various analyses suggest that the underdensity could account for part, but not all of the Hubble tension. No one expects, on first encountering modern cosmology, that the precise measurement of the cosmic expansion rate would lead to a substantial disagreement between two different measurement approaches. No one predicts that the disagreement would persist for a decade without satisfactory resolution. Absolutely no one anticipates the way the Hubble tension has become one of the most studied open problems in modern cosmology, with implications for essentially every aspect of the standard cosmological model, including the cosmic age itself. The implications for the cosmic age are direct. The standard cosmic age value of 13.8 billion years is derived using the Planck-Hubble constant of 67 kilometers per second per megaparsec. If the actual cosmic Hubble constant is closer to the local value of 73 kilometers per second per megaparsec, the cosmic age would be somewhat younger than the standard value, approximately 12.8 billion years. If the actual cosmic Hubble constant is somewhere intermediate between the two measurements, the cosmic age would be somewhere intermediate. The various possibilities produce a substantial range of possible cosmic age values. Pattern interrupt. The intriguing aspect of the new physics resolutions is that some of them produce cosmic ages that are older rather than younger than the standard value. The early dark energy models can, in some specific implementations, produce cosmic ages of 15 to 16 billion years. The varying dark energy models can produce similar results. The cosmic age, considered as a free parameter that depends on the specific cosmological model, is therefore not strictly constrained to the standard 13.8 billion year value. Alternative models that are consistent with the available data can produce substantially older cosmic ages. The takeaway is that this is part of why the Hubble tension is relevant to the cosmic age question. The Hubble tension is not just a curiosity about expansion rate measurements, it is a fundamental challenge to the standard cosmological model that may require new physics to resolve. Any new physics that resolves the Hubble tension will, in general, modify the derived cosmic age as well. The cosmic age value is, in this sense, only as certain as the standard cosmological model from which it is derived. If the standard model needs modification, the cosmic age value needs to be reconsidered. The recent DESI Year 1 results released in 2024 by the Dark Energy Spectroscopic Instrument Collaboration have provided new constraints on dark energy that are relevant to the Hubble tension. The DESI results suggest that dark energy may be slightly time-varying rather than being a true cosmological constant. The implications for the cosmic age depend on the specific time variation, with various analyses producing different specific predictions. The DESI program will continue for several more years, with additional data releases expected to substantially refine our understanding of dark energy and its implications for the broader cosmological model. Tonight, we're going to spend a careful pass on the specific physics of the Hubble tension and the various proposed resolutions, because the tension is one of the most studied open problems in modern cosmology, and the details of the proposed resolutions deserve careful examination. The basic situation is this: the Hubble constant is the present-day expansion rate of the cosmos, conventionally expressed in units of kilometers per second per megaparsec. The Hubble constant value has profound implications for essentially every aspect of cosmology, including the cosmic age, the cosmic size, the cosmic structure formation history, and the cosmic future. The Hubble constant can be measured through two main approaches. The local approach uses nearby objects whose distances can be measured directly. The most precise local approach is the cosmic distance ladder developed by Edwin Hubble and progressively refined over the past century. The modern implementation of the cosmic distance ladder is the SH0ES collaboration, led by Adam Rees at Johns Hopkins University. The SH0ES program has been operating for approximately 2 decades and has progressively refined the Hubble constant measurement. What surfaces from this is that the cosmic microwave background approach uses the temperature variations in the cosmic microwave background, combined with the standard cosmological model, to derive the various cosmological parameters. The most precise cosmic microwave background measurements come from the Planck satellite. The Planck mission produced the most precise full-sky measurements of the cosmic microwave background ever obtained, with the data being analyzed by various groups within the Planck collaboration to produce the standard cosmological parameter values. Pattern interrupt. The two approaches give Hubble constant values that disagree by approximately 9%. The local SH0ES value is approximately 73 kilometers per second per megaparsec. The cosmic microwave background Planck value is approximately 67 kilometers per second per megaparsec. The disagreement is statistically very significant. Both measurements have been progressively refined over the past decade. The disagreement has not gone away. If anything, it has solidified as the measurements have been refined. The disagreement has substantial implications. The Hubble constant value enters into essentially every cosmological calculation. The cosmic age is derived from the Hubble constant combined with the other cosmological parameters. The cosmic size is derived from similar combinations. The cosmic structure formation history depends on the Hubble constant. The cosmic future evolution depends on the Hubble constant. A disagreement at the 9% level in the Hubble constant therefore implies disagreements at similar levels in essentially every derived cosmological quantity. What follows from this is that the proposed resolutions of the Hubble tension fall into several broad categories. The first category invokes systematic errors in one of the measurements. Various aspects of the local distance ladder have been examined for possible systematic errors. The Cepheid variable calibration has been examined. The absolute distance scale derived from Gaia parallax measurements has been examined. The standardization of type Ia supernovae has been examined. None of the various systematic error investigations has identified any specific issue that would explain the full magnitude of the disagreement. Similar investigations have been performed for the cosmic microwave background measurements. The Planck data analysis has been examined for possible systematic issues. The cosmological parameter extraction procedures have been examined. The interpretation of specific features in the cosmic microwave background has been examined. None of the various investigations has identified any specific issue that would resolve the tension. The second category invokes new physics that would modify the cosmic expansion history in ways that affect the two measurements differently. The proposals are diverse. They include time-varying dark energy, in which the dark energy density evolves over cosmic time. They include early dark energy, in which there was a brief period of additional cosmic acceleration shortly before the cosmic microwave background was emitted. They include exotic interactions in the dark sector, in which dark matter and dark energy interact in specific ways. They include modifications to general relativity at cosmic scales. They include various other possibilities. Walk with me through one specific new physics proposal. The early dark energy proposal involves the addition of a new component to the cosmological framework, with the component being dynamically important for a brief period around the time of cosmic microwave background emission. The component contributes to the cosmic expansion rate during the brief period when it is active, modifying the relationship between the various cosmological parameters that the cosmic microwave background measurement constrains. The early dark energy proposal has been worked out in detail by various groups, including the work of Vivian Polan and his collaborators. The detailed analysis shows that early dark energy can, in principle, resolve the Hubble tension without conflicting with most of the other available cosmological data. The proposal has received substantial published attention and has been evaluated against various specific cosmological observations. The empirical status of early dark energy is mixed. Some specific tests have been consistent with the proposal. Other tests have been challenging. The overall situation is one in which the proposal is not clearly ruled out by the available data, but is also not clearly favoured. The proposal remains one of the leading candidates for the Hubble tension resolution, but has not gained broad acceptance as the definitive answer. Step back, and you can see that the other new physics proposals have similar status. Various time-varying dark energy proposals have been advanced and evaluated. Various dark sector interaction proposals have been advanced and evaluated. Various modified gravity proposals have been advanced and evaluated. Each of the proposals has produced specific predictions that can be tested against the available data. The collective effect of the various proposals is that no single proposal has yet emerged as the clear best candidate for the Hubble tension resolution. The third category of resolutions invokes the possibility of a local underdensity. If the local cosmic region has somewhat lower density than the cosmic average, the local Hubble constant measurement would be biased upward relative to the global cosmic average. The underdensity proposal has been worked out in detail by various groups, with the resulting analyses suggesting that the underdensity could account for some but not all of the Hubble tension. The specific empirical evidence for a local underdensity is mixed. Some surveys have suggested that the local cosmic region is somewhat underdense compared to the global average. Other surveys have suggested that the local density is essentially typical. The various measurements have substantial systematic uncertainties, with the detailed picture not being fully resolved. No one expects, on first encountering modern cosmology, that the question of the cosmic expansion rate would have such substantial implications for so many different aspects of the broader cosmological framework. No one predicts that a single 9% disagreement would lead to such extensive investigation of so many different theoretical and empirical possibilities. Absolutely no one anticipates the way the Hubble tension has become one of the most empirically and theoretically active areas in modern cosmology. Pattern interrupt. The implications for the cosmic age are direct and substantial. The cosmic age depends on the Hubble constant in specific ways. A modified cosmological framework that resolves the Hubble tension will, in general, modify the derived cosmic age as well. Different specific resolution frameworks produce different specific cosmic age predictions, with the values spanning a substantial range. The cosmic age value is, in this sense, only as certain as the underlying cosmological framework. If the framework needs modification to resolve the Hubble tension, the cosmic age value needs to be reconsidered. The recent DSE Year 1 results released in 2024 have provided new constraints on dark energy that are relevant to the Hubble tension. The DSE results suggest that dark energy may be slightly time-varying rather than being a true cosmological constant. The implications for the Hubble tension depend on the specific time variation, with the analysis being substantially advanced by the DSE program. The subsequent DSE data releases expected over the coming years will substantially refine the constraints on dark energy and on the broader cosmological framework. Hold this image. The Hubble tension is one of the most studied open problems in modern cosmology. The disagreement between local and cosmic microwave background measurements has not been satisfactorily resolved after a decade of careful work. The proposed resolutions involve substantial modifications to the standard cosmological framework, with the modifications producing different specific predictions for the various cosmological parameters, including the cosmic age. The cosmic age value is, in this sense, more uncertain than the standard derivation suggests. Hold this image. The Hubble tension is one of the most studied open problems in modern cosmology. The disagreement between local and cosmic microwave background measurements of the Hubble constant is substantial and has not been satisfactorily explained. The proposed resolutions, particularly those involving new physics, have substantial implications for the cosmic age. The cosmic age value, considered carefully, is not strictly fixed at the standard 13.8 billion year value. Alternative cosmological models that successfully resolve the Hubble tension can produce substantially older cosmic ages. The work continues. The fourth reason the cosmic age may need revision is one of the more empirically striking features of the modern cosmological data. Supermassive black holes have been observed at very early cosmic times, with masses that are difficult to explain through the standard formation mechanisms within the available cosmic time. Tonight, we're going to walk into this carefully, because the early supermassive black hole puzzle is one of the most consequential observational results to emerge from the James Webb era. The basic situation is this: every large galaxy in the modern universe contains a supermassive black hole at its center, with mass typically in the range of 1 million to 10 billion solar masses. The Milky Way's central black hole, Sagittarius A star, has a mass of approximately 4 million solar masses. The Andromeda Galaxy's central black hole has a mass of approximately 100 million solar masses. The most massive central black holes, located in the centers of giant elliptical galaxies, have masses exceeding 10 billion solar masses. The standard story of how these supermassive black holes formed involves a slow growth process over cosmic time. The basic mechanism starts with a stellar mass seed black hole formed from the death of a massive star. The seed black hole accretes matter from its surrounding gas environment, gradually growing through the process. The accretion is limited by the Eddington limit, which sets the maximum rate at which a black hole can accrete matter under standard conditions. At the Eddington limit, the black hole's mass doubles approximately every 50 million years. What this leaves us with is that the implications for the cosmic time required to grow a supermassive black hole from a stellar mass seed. To grow from 100 solar mass seed to a 1 million solar mass black hole requires approximately 14 doublings, taking about 700 million years at the Eddington limit. To grow to a billion solar mass black hole requires approximately 23 doublings, taking about 1.15 billion years at the Eddington limit. The cosmic time required for the growth depends on the specific seed mass and the specific accretion history. Catch the texture of this. The James Webb observations have detected supermassive black holes at cosmic times that, by the standard accretion timescales, would not have been sufficient for the observed masses to have been achieved. The galaxy GNZ11 observed at a redshift of approximately 10.6, corresponding to a cosmic time of about 420 million years after the Big Bang, contains a supermassive black hole of approximately 1 to 2 million solar masses. The cosmic time available for the black hole growth is less than the time required at the standard Eddington limit accretion rate. Now, let's begin to consider implications. The implications are direct. Either the standard accretion process operated at faster rates than the Eddington limit allows, or the seed black holes were substantially more massive than ordinary stellar mass seeds, or both, or the cosmic time available for the growth was somewhat longer than the standard timeline allows. The mainstream interpretation invokes some combination of super-Eddington accretion and direct collapse seed mechanisms. The super-Eddington accretion proposal suggests that the standard Eddington limit can be exceeded under specific conditions, allowing faster mass growth. The direct collapse seed proposal suggests that some early black holes formed directly from the collapse of massive gas clouds, with initial masses of tens of thousands to hundreds of thousands of solar masses. The combination of the two mechanisms can, in principle, account for the observed early supermassive black hole population. What this picture tells us is that the mainstream interpretation has both strengths and limitations. The strength is that both mechanisms have been worked out in detail by theoretical groups and have been shown to be physically possible under specific conditions. The limitation is that the specific conditions required for the mechanisms to operate efficiently in the early universe have not been independently confirmed, and the observed early supermassive black hole population requires both mechanisms to have operated at fairly substantial rates. Walk with me through the alternative interpretation. If the cosmic age is older than the standard 13.8 billion year value, then the cosmic time available for black hole growth at any given redshift is longer than the standard calculations suggest. The black holes observed at high redshifts would have had more time to grow than the standard timeline allows. The observed masses could be more easily accommodated within the modified framework without requiring either super-Eddington accretion or direct collapse seed mechanisms to operate at extreme rates. The alternative interpretation has been advanced by various researchers as part of the broader case for cosmic age revision. The interpretation is consistent with the observed black hole masses without requiring the specific physical mechanisms invoked by the mainstream interpretation. The interpretation does not, by itself, prove that the cosmic age needs revision, but it provides one piece of empirical input that is consistent with such a revision. The specific case of GNZ11 has received substantial attention in this context. The galaxy was originally identified by Hubble Space Telescope observations and was subsequently studied in detail by James Webb. The detailed analysis published by Roberto Maiolino at the University of Cambridge and his collaborators in 2024 established the black hole mass with high precision and confirmed that the black hole is genuinely too massive for its cosmic age under the standard formation mechanisms. No one expects, on first thinking about cosmic black hole assembly, that the question of supermassive black hole origins would have implications for the cosmic age itself. No one predicts that the observed early supermassive black hole population would be consistent with multiple different interpretations of the broader cosmological framework. Absolutely no one anticipates the way the empirical study of high redshift active galactic nuclei has become one of the more empirically rich sources of input on the cosmic age question. The implications for the broader picture of cosmic structure formation are substantial. The early supermassive black holes are part of the broader pattern of structure formation in the early universe that James Webb has been revealing. The observed galaxies are too developed, the observed black holes are too massive, the observed chemistry is too enriched. The combined empirical picture is one of structure formation that proceeded faster than the standard models allowed. The mainstream interpretation involves various refinements to the structure formation models. The alternative interpretation involves cosmic age revision. The distinction between the two interpretations is not yet resolvable from the available data. The James Webb program will continue to operate for at least another decade, with the additional data expected to substantially refine the empirical picture. The combination of James Webb data with the planned Roman Space Telescope observations, the ongoing Euclid observations, and the DESI Dark Energy program will, by the early 2030s, provide a much more constrained picture of both the early cosmic structure formation and the broader cosmological framework. Notice the shift. The empirical work, in this sense, is ongoing. The cosmic age question is not yet resolved. The various lines of evidence we have walked through tonight, including the high redshift galaxy observations, the Methuselah star ages, the Hubble tension, and the early supermassive black holes, all point in the same general direction. They suggest that either the cosmic timeline needs to be modified to allow more time for structure formation at any given redshift, or that the various structure formation mechanisms need to operate at substantially faster rates than the standard models allow. The work of distinguishing between these possibilities is being conducted in real time by the broader cosmology community. The point worth taking away is that this is part of why the early supermassive black hole question is empirically valuable. The question is not just a curiosity about specific exotic objects. It is a direct empirical probe of the consistency between the cosmic structure formation framework and the cosmic timeline framework. The two frameworks must produce consistent results for the same physical reality. Any tensions between them indicate that further work is needed in one or both frameworks. Tonight, we're going to walk through the specific physics of supermassive black hole seed formation, because the seed mechanism is the most important uncertainty in the early supermassive black hole question, and the various proposals deserve careful examination. The basic situation is this: the supermassive black holes observed at the centers of modern galaxies must have grown from some specific seed objects in the early universe. The seed objects could, in principle, be of several different types. The simplest type is a stellar mass seed, formed from the death of a single massive star. The seed mass for this type would be in the range of 10 to 100 solar masses, depending on the specific properties of the dying star. The intermediate mass seed type involves black holes formed through processes that produce more massive seeds than ordinary stellar deaths. The two main proposals for intermediate mass seeds are direct collapse black holes and primordial black holes. Direct collapse black holes form from the gravitational collapse of massive gas clouds in the very early universe, without passing through a stellar phase. Primordial black holes form in the very early universe from extreme density fluctuations in the primordial plasma. Notice that the implications of the different seed types for the cosmic time required to grow a supermassive black hole. A stellar mass seed of 100 solar masses growing at the Eddington limit would require approximately 700 million years to reach 1 million solar masses. A direct collapse seed of 100,000 solar masses growing at the same Eddington limit would require only approximately 150 million years to reach the same final mass. A primordial black hole seed of 1,000 solar masses would require an intermediate time. Hold the thought. The observed early supermassive black holes are at cosmic times that constrain the possible seed mechanisms. The galaxy GNZ11, observed at a cosmic time of approximately 420 million years after the Big Bang, contains a supermassive black hole of approximately 1 to 2 million solar masses. The cosmic time available for the black hole growth is approximately 300 to 400 million years, assuming the seed black hole formed shortly after the first stars. The available time is sufficient for direct collapse seed growth at the Eddington limit, but is tight for stellar mass seed growth. The implications depend on which specific scenario actually operated. If the seed was a direct collapse black hole, the standard accretion processes can plausibly produce the observed mass within the available time. If the seed was a stellar mass black hole, super Eddington accretion would be required. The direct collapse black hole scenario has been the subject of substantial theoretical work over the past 2 decades. The leading theoretical groups include Marta Volonteri at the Institut d'Astrophysique de Paris, Mitchell Begelman at the University of Colorado, and Zoltan Hyman at Columbia University. The various analyses have established that direct collapse is, in principle, physically possible under specific conditions in the early universe. What this means is that the specific conditions required for direct collapse are demanding. The collapsing gas cloud must have a mass of at least several million solar masses. The cloud must be at very low metallicity, because heavy elements would provide cooling channels that would cause the cloud to fragment into many small stars instead of producing a single massive object. The cloud must be exposed to strong ultraviolet radiation that destroys molecular hydrogen, the dominant cooling channel in primordial gas. The combination of these conditions is rare but not impossible in the very early universe. The empirical signatures of direct collapse seeds have been the subject of substantial observational work. The James Webb observations have begun to identify candidate intermediate mass black holes that could be the immediate descendants of direct collapse seeds. The identifications are still tentative, but the pattern is consistent with the direct collapse scenario operating at substantial rates in the early universe. The primordial black hole scenario has also been studied extensively. The proposal that black holes could have formed in the very early universe before the first stars existed was originally advanced by Stephen Hawking and Bernard Carr in the 1970s. The proposal has been revived in recent years, partly as a potential explanation for the early supermassive black hole population. Walk with me through one specific aspect of the primordial black hole scenario. The mass spectrum of primordial black holes depends on the specific conditions in the very early universe. Different inflationary models, different early universe phase transitions, and different other specific physical processes produce different predictions for the primordial black hole mass spectrum. Some specific models predict primordial black holes in the mass range relevant for supermassive black hole seeds. The empirical constraints on primordial black holes have been progressively refined over the past several decades. The various observational tests have established that primordial black holes cannot dominate the cosmic dark matter, but they allow a substantial subdominant population in various specific mass ranges. The mass range relevant for supermassive black hole seeds, approximately 100 to 10,000 solar masses, is not strongly constrained by the current observations. The primordial black hole scenario therefore remains empirically viable as a contributor to the supermassive black hole seed population. No one expects, on first thinking about cosmic black hole assembly, that the question of supermassive black hole origins would involve such substantial theoretical and empirical uncertainty. No one predicts that the early supermassive black holes observed by James Webb would have multiple, potentially viable seed mechanisms, with the choice between them depending on specific aspects of the early universe physics. Absolutely no one anticipates the way the supermassive black hole seed question has become so directly connected to the broader cosmic age question. The implications for the cosmic age question are substantial. If the cosmic age is older than the standard value, the cosmic time available for supermassive black hole growth at any given redshift is longer than the standard calculations suggest. The growth could proceed more comfortably from stellar mass seeds at the Eddington limit, without requiring either direct collapse seeds or super-Eddington accretion. The empirical case for the alternative seed mechanisms would be weakened, while the case for cosmic age revision would be strengthened. A slow turn. The opposite logic also applies if the cosmic age is firmly the standard 13.8 billion year value. The empirical case for either direct collapse seeds or super-Eddington accretion is strengthened. The various theoretical proposals for these specific mechanisms are then more directly empirically motivated. The relationship between the cosmic age question and the seed mechanism question is, in this sense, bidirectional. Either question can inform the other. What emerges from this is that the empirical resolution of the supermassive black hole seed question is, in this sense, partly dependent on the empirical resolution of the cosmic age question. The two questions are connected through the cosmic time available for black hole growth. The next decade of observational work, including continued James Webb observations and additional data from various other programs, will progressively address both questions simultaneously. Hold this image. The supermassive black hole seed question is one of the more empirically active areas in modern cosmology. The various proposed seed mechanisms have substantially different implications for the cosmic time required for supermassive black hole growth. The connection to the cosmic age question is direct, with the empirical resolution of the seed question being partly dependent on the empirical resolution of the cosmic age question. The work continues, with substantial additional progress expected over the coming decade. Hold this image. Supermassive black holes have been observed in the very early universe at cosmic times when the standard formation mechanisms would not have allowed their full development. The observed black holes are, by every available analysis, too massive for their cosmic ages. The mainstream interpretation involves invoking specific physical mechanisms including super-Eddington accretion and direct collapse seeds. The alternative interpretation involves cosmic age revision. The empirical work to distinguish between these possibilities continues, with substantial additional input expected from the next decade of observational programs. The fifth reason the cosmic age may need revision is that alternative cosmological models have been published that propose substantially older cosmic ages while remaining consistent with most of the available observational data. Tonight, we're going to walk into these alternatives carefully because the existence of viable alternative models is one of the more empirically substantial considerations in the broader cosmic age question. The basic situation is this: the standard cosmological model called lambda cold dark matter, or lambda CDM, has been the dominant theoretical framework for understanding the cosmos for approximately 3 decades. The model includes specific assumptions about the nature of dark matter, the nature of dark energy, the geometry of the cosmos, and various other parameters. The model has been successful at explaining a wide range of cosmological observations, including the cosmic microwave background, the large-scale distribution of galaxies, the cosmic expansion history, and the abundance of light elements produced in Big Bang nucleosynthesis. The standard cosmic age value of 13.8 billion years is derived within the lambda CDM framework. The derivation involves combining the Planck cosmic microwave background measurements with the standard model assumptions to extract the various cosmological parameters. The cosmic age, like the various other parameters, depends sensitively on the specific assumptions of the framework. Different cosmological frameworks would produce different specific values for the cosmic age, even when fitted to the same underlying observational data. What becomes clear is that this opens up the possibility of alternative cosmological models that produce different cosmic age values. The alternatives have been proposed by various researchers over the past several decades, with the proposals progressively becoming more sophisticated as the observational data has accumulated. The most prominent recent proposal which has received substantial published attention is the work of Rajendra Gupta at the University of Ottawa. Let the picture settle. Gupta proposed a modified cosmological model in 2023 that incorporates 2 specific modifications to the standard framework. The first modification involves tired light, the proposal that light loses energy as it travels through space due to a specific physical process not accounted for in the standard framework. The second modification involves varying coupling constants, the proposal that the fundamental constants of physics may vary over cosmic time. The combination of these 2 modifications, when fitted to the available observational data, produces a cosmic age of approximately 26.7 billion years, nearly twice the standard value. Now, let's begin. The Gupta model has been published in mainstream journals including monthly notices of the Royal Astronomical Society and the Astrophysical Journal. The papers have received substantial peer review and have been accepted for publication based on the technical merits of the analyses. The model has received serious attention from some cosmologists who have evaluated the proposals against the available data and found them consistent with substantial portions of the observational record. The takeaway is that the Gupta model remains a minority view within the broader cosmology community. The mainstream view continues to favor the standard lambda CDM framework, with the cosmic age value of 13.8 billion years being treated as the best current estimate. The minority view that the cosmic age may be substantially older is held by a relatively small number of researchers who have evaluated the Gupta model and similar alternatives and found them potentially viable. The objections to the Gupta model are substantial and have been articulated by various cosmologists. The tired light proposal in particular has been previously considered and rejected by the broader community on the grounds that it produces specific predictions that disagree with various observational constraints. The varying coupling constant proposal has similarly been previously considered and rejected on similar grounds. The combination of the two proposals in the specific form Gupta has developed may avoid some of the previous objections, but the model remains controversial within the broader cosmology community. Walk with me through one specific aspect of the Gupta model. The model proposes that the cosmic redshift, the apparent stretching of light from distant galaxies, is partially due to tired light energy loss and partially due to the cosmic expansion. The standard interpretation attributes the redshift entirely to cosmic expansion, with the implications for the cosmic age depending on the specific expansion history. The Gupta interpretation modifies the relationship between observed redshift and cosmic time, with the implications including a substantially older cosmic age. The empirical tests of the Gupta model have been mixed. Some specific tests have been consistent with the model's predictions. Other tests have been challenging for the model. The overall situation is one in which the model is not clearly ruled out by the available data, but is also not clearly favoured over the standard framework. The model remains a minority alternative that has received some serious attention, but has not gained broad acceptance. What surfaces from this is that the broader picture of alternative cosmological models includes various other proposals beyond the Gupta model. Various early dark energy models, when fitted to specific observational constraints, can produce cosmic ages somewhat older than the standard value. Various modified gravity proposals can produce different cosmic ages. The combined collection of alternative proposals spans a substantial range of possible cosmic age values, with the standard 13.8 billion year value being one specific outcome, among many possible alternatives. The implications for our broader confidence in the standard cosmic age are substantial. The standard value is the best current estimate within the standard cosmological framework. The standard framework is the best current model based on the available data. But the framework is not the only viable theoretical possibility. Alternative frameworks that produce different cosmic ages are technically possible and have been published by serious researchers. The cosmic age value is, in this sense, more uncertain than the formal 1% precision of the standard derivation suggests. No one expects, on first thinking about modern cosmology, that the cosmic age would have multiple, potentially viable estimates within the published literature. No one predicts that alternative cosmological models would produce cosmic age estimates substantially different from the standard value while remaining consistent with most of the available observational data. Absolutely no one anticipates the way the cosmic age question has become more theoretically open than the popular framing of the standard value suggests. The implications for the broader picture of cosmological certainty are also substantial. The standard cosmological model has been remarkably successful at explaining a wide range of cosmological observations. The success has been treated as strong evidence that the standard framework is essentially correct. But the success does not strictly require that the framework is unique. Alternative frameworks that explain the same observations are technically possible, and the existence of such frameworks suggests that the cosmological parameters derived from the standard framework should be held with somewhat less confidence than the formal uncertainties suggest. Mark this moment. The recent observational tensions, including the high redshift galaxy observations, the Methuselah star ages, the Hubble tension, and the early supermassive black holes, all provide empirical input that is consistent with several different theoretical interpretations. The mainstream interpretation involves refinements to the standard framework. Various alternative interpretations involve different specific changes. The empirical question of which interpretation is correct is still being investigated, with substantial work expected over the coming years. What follows from this is that the cosmic age question is, in this sense, more empirically and theoretically open than the standard 13.8 billion year value suggests. The standard value is the best current estimate within the standard framework. Alternative frameworks are technically possible. The various observational tensions provide empirical input that is consistent with multiple theoretical interpretations. The work of distinguishing between the alternatives continues. The next decade of cosmological work is expected to substantially advance our understanding of the various open questions. The Roman Space Telescope, planned for launch in 2027, will provide much more comprehensive measurements of high redshift galaxies. The DESI program will provide much more precise constraints on dark energy. The Vera Rubin Observatory, currently coming online, will provide much more precise measurements of the cosmic expansion history. The combined effect of these various programs will, by the early 2030s, provide substantial additional constraints on the cosmic age question. Tonight, we're going to spend a careful pass on the specific structure of the Gupta cosmological model, because the model is the most prominent published alternative to the standard cosmic age, and the details deserve careful examination. The basic situation is this. Rajendra Gupta is a researcher at the University of Ottawa who has been working on cosmological alternatives to the standard Lambda CDM framework for approximately a decade. The work culminated in 2023 with a series of papers proposing a modified cosmological model that gives a cosmic age of approximately 26.7 billion years, almost twice the standard value. The papers were published in mainstream journals, including monthly notices of the Royal Astronomical Society and the Astrophysical Journal. The Gupta model incorporates two specific modifications to the standard framework. The first modification involves tired light, the proposal that light loses energy as it travels through space due to a specific physical process not accounted for in the standard framework. The second modification involves varying coupling constants, the proposal that the fundamental constants of physics may vary over cosmic time. The combination of these two modifications, when fitted to the available observational data, produces the substantially older cosmic age. Step back, and you can see that the tired light proposal has a long and contested history in cosmology. The original tired light proposal was advanced by Fritz Zwicky in 1929, shortly after Edwin Hubble's discovery of the cosmic expansion. Zwicky proposed that the observed redshift of distant galaxies could be due, at least in part, to light losing energy as it travelled through space, rather than being due entirely to the cosmic expansion. The proposal was an alternative to the cosmic expansion interpretation that the broader community eventually accepted. Stay with this thought. The original tired light proposal was extensively examined and largely rejected over the subsequent decades. The various empirical tests included the time dilation of distant supernova light curves, the surface brightness scaling of distant galaxies, the cosmic microwave background existence and properties, and various other observational features. The simple, tired light proposal produces predictions for these features that disagree with the available data, leading to the broad community rejection of the proposal. The Gupta model incorporates a modified version of tired light. That, in combination with the varying coupling constant modification, may avoid some of the previous objections. The specific modifications are technical and involve detailed adjustments to the tired light physics. The empirical predictions of the modified model are different from the original tired light predictions in specific ways, with some specific tests being more consistent and others being similar to the original predictions. The varying coupling constant proposal also has a substantial history in cosmology. The proposal that the fundamental constants of physics may vary over cosmic time has been examined empirically through various tests. The fine structure, constant in particular, has been measured at various cosmic distances and at various cosmic times. The measurements have produced mixed results, with some specific tests suggesting possible variations and other tests being consistent with no variation. The current empirical situation is one of substantial uncertainty. What this leaves us with is that the Gupta model combines these two specific proposals in a way that produces specific testable predictions. The model has been fitted to the cosmic microwave background data, the Type Ia supernova data, the galaxy redshift survey data, and various other observational data sets. The fitting procedure produces the best fit cosmic age value of approximately 26.7 billion years, with various other modifications to the other cosmological parameters. The empirical tests of the Gupta model have produced mixed results. Some specific tests have been consistent with the model's predictions. Other tests have been challenging for the model. The overall situation is one in which the model is not clearly ruled out by the available data, but is also not clearly favored over the standard lambda CDM framework. The objections to the Gupta model have been articulated by various cosmologists. The most substantial objection is that the tired light physics, even in the modified form Gupta proposes, has specific predictions that disagree with various observational features. The cosmic microwave background blackbody spectrum in particular is one of the more constraining empirical tests. The standard interpretation of the cosmic microwave background as a relic of the hot, dense, early universe predicts a specific blackbody spectrum that has been measured to extraordinary precision by the COBE-FIRAS instrument. The tired light interpretation must produce a similar spectrum to remain consistent with the observation, and the specific physics required to do so is contested. Walk with me through one specific empirical implication. The Type Ia supernova light curves have specific time dilation properties that depend on the source distance. At larger distances, the light curves are stretched in time by the cosmic expansion. The time dilation effect has been measured precisely and is consistent with the standard cosmic expansion interpretation. The tired light interpretation must produce the same time dilation effect to remain consistent with the data, and the specific physics required to do so is also contested. The empirical status of the Gupta model is therefore mixed. The model is consistent with some specific observational tests. The model is challenging for other specific tests. The overall situation is one of substantial controversy within the broader cosmology community. The model has received serious published attention, but has not gained broad acceptance. No one expects, on first thinking about modern cosmology, that the cosmic age would have such a substantially different alternative published value as the Gupta model proposes. No one predicts that a specific alternative model would give a cosmic age nearly twice the standard value while remaining consistent with substantial portions of the available data. Absolutely no one anticipates the way the cosmic age question has become so theoretically open in the contemporary cosmological literature. Settle in here. The implications for our broader confidence in the standard cosmic age are nuanced. The Gupta model is a minority view, not a definitive alternative. The standard lambda CDM framework remains the consensus view. But the existence of published alternative models with significantly different cosmic age values suggests that the cosmic age estimate is more uncertain than the formal 1% precision of the standard derivation suggests. The genuine theoretical uncertainty is larger than the formal precision indicates. What this picture tells us is that this is part of the broader picture of why the cosmic age question is genuinely open. The standard value is the best current estimate within the standard framework. Alternative frameworks are technically possible and have been published. The empirical work to distinguish between the alternatives continues, with the various observational tensions providing empirical input that is consistent with multiple interpretations. The cosmic age value in this sense has not been fully settled. Hold this image. The Gupta cosmological model is one specific alternative to the standard lambda CDM framework that produces a substantially older cosmic age. The model has been published in mainstream journals and has received serious peer review. The model remains a minority view within the broader cosmology community, with substantial objections having been articulated. But the existence of the model demonstrates that the cosmic age value is more theoretically open than the standard derivation suggests, with alternative frameworks producing substantially different specific values. Hold this image. The cosmic age question is, in this sense, genuinely open in ways that the standard 13.8 billion-year value does not fully convey. The standard value is the best current estimate within the standard framework. Alternative frameworks produce different specific values. The various recent observational tensions provide empirical input that is consistent with multiple theoretical interpretations. The work of distinguishing between the alternatives continues, with substantial progress expected over the coming years as additional observational data accumulates. Tonight, we're going to spend a careful pass on what the various open questions about the cosmic age imply for the broader picture of cosmological certainty, because the implications extend beyond the specific cosmic age value to broader questions about how confident we should be in the various fundamental cosmological parameters. Before we get started, sit with the basic situation. The standard cosmological model has been extraordinarily successful at explaining a wide range of observational data. The success has been treated in the popular discussion and in much of the technical literature as strong evidence that the standard framework is essentially correct. The cosmic age value, like the various other cosmological parameters, has been treated as one of the more confident determinations that modern cosmology has been able to make. The empirical situation, however, is more complicated than the standard framing suggests. The various tensions we have walked through tonight, including the high redshift galaxy observations, the Methuselah star ages, the Hubble tension, the early supermassive black holes, and the existence of viable alternative cosmological models, all suggest that the standard framework may need refinement in specific ways. The refinements could affect the various cosmological parameters, including the cosmic age. The point worth taking away is that this has substantial implications for how we should think about cosmological certainty more broadly. The standard cosmological framework is the best current theoretical model based on the available data. The standard framework is not the only viable theoretical possibility. Alternative frameworks are technically possible and have been published. The genuine uncertainty in the cosmological parameters is therefore larger than the formal uncertainties within the standard framework suggest. Hold this image. The implications for the cosmic age specifically are direct. The cosmic age value depends on the cosmological framework used to derive it. The standard framework gives 13.8 billion years. Alternative frameworks give different specific values ranging from somewhat younger to substantially older. The actual cosmic age is, in principle, some specific value, but our current best estimate of that value is more theoretically and empirically open than the standard value suggests. The implications for the broader picture of cosmic certainty are similarly substantial. The standard cosmological framework has been remarkably successful, but the success has been within specific empirical and theoretical constraints. The framework has been tested against the available data and has been found to be consistent with substantial portions of that data. The framework has not been tested against the full theoretical possibility space, which includes various alternative frameworks that produce somewhat different predictions for various specific tests. Walk with me through one specific implication. The cosmic age value enters into essentially every cosmological calculation: the cosmic size, the cosmic structure formation history, the cosmic expansion history, the cosmic future, evolution, all depend in specific ways on the cosmic age. A revision to the cosmic age would propagate through essentially every aspect of cosmology. The implications would extend across multiple research areas, with substantial work being required to rederive the various standard results within the modified framework. The implications for our understanding of cosmic history are also substantial. The standard cosmic history has the Big Bang occurring approximately 13.8 billion years ago. The first stars ignited approximately 100 million years after the Big Bang. The cosmic dawn era occurred during the subsequent few 100 million years. The active stelliferous epoch began at that time and continues to the present. The standard history is well established within the standard framework. A revised cosmic age would modify this history in specific ways. If the cosmic age is older, the Big Bang occurred earlier, and the various subsequent epochs may have had longer duration. The first stars may have formed earlier, allowing more time for the development of the cosmic chemical inventory. The cosmic dawn era may have been more extended, allowing more time for the various structure formation processes to operate. The active stelliferous epoch may have begun earlier, allowing more cosmic time for the various stellar processes to have operated. Notice that this is, in some sense, why the cosmic age question is so foundationally important. The cosmic age is one of the most fundamental cosmological parameters. The value of the cosmic age affects essentially every aspect of cosmological understanding. The question of whether the cosmic age value is correctly determined is therefore not just a technical question. It is a foundational question that affects the broader picture of cosmic history and cosmic future. There is something genuinely interesting about being alive during this particular phase of cosmological work. The standard cosmological model has dominated theoretical thinking for approximately 3 decades. The model has been remarkably successful, but the recent observational tensions suggest that some refinements may be needed. The next decade of cosmological work will substantially clarify the situation, with the cosmic age value either being confirmed at the standard value or being revised to some specific, different value. No one expects, on first thinking about modern cosmology, that the question of the cosmic age would still be sufficiently open to allow serious discussion of substantially older alternative values. No one predicts that the empirical observations would have produced such substantial tensions with the standard framework over the past several years. Absolutely no one anticipates the way the contemporary moment in cosmology is one of substantial active reconsideration of foundational questions that had been treated as essentially settled. Expectation. The cosmic age is one of the more confident cosmological parameters, with the standard value being essentially settled. Reality. The cosmic age is more uncertain than the standard framing suggests, with various empirical and theoretical considerations consistent with substantially different specific values. The implications for thinking about cosmic value are interesting. The cosmic configurations we observe are characteristic of the active, stelliferous epoch within the standard cosmological framework. The standard framework treats the cosmic configurations as representative of cosmic time within specific assumptions. A revised framework with substantially different cosmic age would modify the interpretation of cosmic configurations in specific ways. The various aspects of cosmic experience that depend on the cosmic age would be affected in specific ways. Notice the turn. The implications for thinking about cosmic typicality are also substantial. The standard framework treats the current cosmic configuration as the result of approximately 13.8 billion years of cosmic evolution. A revised framework with longer cosmic age would treat the current configuration as the result of substantially longer evolution. The specific implications depend on the specific revised framework, but the broader picture is that our position in cosmic history is more uncertain than the standard framing suggests. What this means is that this is part of why the cosmic age question is so foundationally important. The question affects how we think about our position in cosmic history. The question affects how we think about the cosmic environment we inhabit. The question affects how we think about the broader cosmic story that our existence is part of. The cosmic age value is, in this sense, more than just a technical parameter. It is a foundational element of how we understand our cosmic context. Hold this thought. The cosmic age question is genuinely open in ways that the standard textbook framing does not fully convey. The standard value is the best current estimate within the standard framework. Alternative frameworks produce substantially different values. The empirical tensions we have walked through tonight provide input that is consistent with multiple interpretations. The work of distinguishing between the alternatives continues, with substantial progress expected over the coming years. What this leaves us with is a sense of why the cosmic age question matters beyond just the technical value. The question is foundational. The question affects multiple aspects of cosmological understanding. The question is currently being substantially reconsidered by the broader cosmology community. We are alive at a moment when this reconsideration is being actively conducted, with the outcomes substantially shaping the textbook chapter on cosmic history that future generations will inherit. Tonight, we're going to address 5 common misconceptions about the cosmic age question directly. because each one is widely repeated and each one deserves a careful correction. Now, let's begin with the first misconception. The misconception is that the cosmic age has been definitively revised to a substantially different value. The claim sometimes appears in viral discussions citing the Gupta model and similar work as evidence that the standard cosmic age is wrong. The technical reality is more measured. The Gupta model is a published alternative that has received serious peer review, but it remains a minority view within the broader cosmology community. The mainstream cosmological view continues to favor the standard 13.8 billion year value, with the various tensions being attributed to specific aspects of the cosmological framework that may need refinement rather than to a fundamental error in the cosmic age value. No one expects, on first hearing the popular framing, that the gap between the dramatic revisions sometimes claimed in viral discussions and the actual scientific situation could be quite this large. No one predicts that the alternative cosmic age proposals would be presented in popular contexts as essentially definitive when they remain minority views. Absolutely no one anticipates the way the popular discussion has substantially mischaracterized the actual state of the cosmic age question. Before we get started on the second misconception, sit with why the first one persists. Dramatic revisions are attention-grabbing. Measured technical discussions are not. The popular framing has, predictably, favored the dramatic version even though it does not match the actual technical situation. Now, let's begin with the second misconception. The misconception is that the JWST observations have proven the standard model is wrong. The claim sometimes appears in popular contexts that depict the recent JWST data as essentially refuting lambda CDM. The technical reality is more measured. The JWST observations have produced empirical tensions with specific aspects of the standard galaxy formation models. The tensions have not refuted the broader lambda CDM framework. No one predicts the framework's continued utility despite the tensions. The framework continues to be used because it remains the best current theoretical model for the broader cosmological observations. What emerges from this is that this distinction matters. The popular framing of JWST as refuting the standard model is technically incorrect. Expectation, the popular framing. Reality, the actual situation is that JWST has produced empirical tensions with specific predictions of the standard galaxy formation models, with the broader cosmological framework continuing to be considered the best current approach. The tensions are real and significant, but they are tensions within the framework rather than refutations of the framework. The third misconception is that the Methuselah star ages prove the cosmic age is wrong. The claim sometimes appears in popular contexts, citing HD 140-0283 as evidence that the universe is older than the standard value. The technical reality is more measured. The Methuselah star age estimates approach or slightly exceed the standard cosmic age, with uncertainties that allow both possibilities. The estimates are uncomfortably close to the cosmic age but do not strictly require cosmic age revision. The mainstream interpretation involves systematic uncertainties in the stellar age estimates, rather than cosmic age revision. Expectation. The Methuselah stars prove the universe is older than 13.8 billion years. Reality. The Methuselah stars have age estimates that are uncomfortably close to the standard cosmic age, with the situation being genuinely uncomfortable but not strictly impossible within the standard framework. The fourth misconception is that the Hubble tension is a simple disagreement that can be easily resolved. The The claim sometimes appears in popular contexts that depict the Hubble tension as a technical issue that will likely be resolved through better measurements or through minor adjustments. The technical reality is more substantial. The Hubble tension has persisted for over a decade, despite substantial work to resolve it. Both measurements have been progressively refined. The tension has solidified rather than dissolving. The resolution likely requires substantial modifications to the standard cosmological framework, with implications for multiple cosmological parameters, including the cosmic age. No one predicts, on first encountering the Hubble tension, that the disagreement would prove this stubborn against multiple decades of resolution attempts. No one expects that the various proposed resolutions would all involve substantial modifications to the standard framework rather than minor technical adjustments. Absolutely no one anticipates the way the Hubble tension has become one of the more empirically and theoretically active areas in modern cosmology. Pause for a moment. The fifth misconception is that the cosmic age question is essentially closed and will not significantly change. The claim sometimes appears in confident popular discussions that present the standard cosmic age as essentially settled. The technical reality is that the cosmic age question is genuinely open at the level of approximately 10 to 20%. The standard value is the best current estimate, but the various tensions and alternative frameworks allow for cosmic age values that range from somewhat younger to substantially older. The next decade of observational work is expected to substantially clarify the situation, with the eventual cosmic age value either being confirmed near the standard value or being revised to some specific, different value. What becomes clear is that this is part of why the cosmic age question is genuinely interesting. The question is not closed. The empirical work continues. The theoretical work continues. The eventual resolution will substantially affect multiple aspects of cosmological understanding. The current moment is one of genuine active reconsideration of foundational questions. Hold this image. 5 misconceptions, each one widely repeated, each one wrong in specific ways. The corrections do not diminish the significance of the cosmic age question as a research topic. The question is genuinely important. The question has substantial implications for the broader cosmological framework. But the popular framings, while attention-grabbing, do not accurately represent the technical situation. The actual situation is more measured and, in some ways, more interesting than any of the popular framings suggest. What this leaves us with is a clearer view of what the cosmic age question actually means, not a settled value that is definitively wrong, not a definitive proof of cosmic age revision, not a simple disagreement that will be easily resolved, not a closed question that will not change. The actual situation is one of genuine active reconsideration, with multiple lines of evidence consistent with multiple interpretations, with the work continuing across the broader cosmology community. Allow me to spend a careful pass on what comes next in cosmology, because the directions of current and planned work are worth knowing, and the next decade promises substantial additional progress on the cosmic age question. Now, let's begin with the first major development to expect. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027 by NASA, will provide substantially more comprehensive measurements of high redshift galaxies than James Webb. Roman will have a field of view approximately 100 times larger than James Webb, with similar sensitivity in the relevant infrared bands. The combination will allow systematic wide-area surveys of high redshift galaxies with statistical samples that will dwarf the current James Webb samples. The Roman observations will be particularly valuable for measuring the number density of bright early galaxies. The current James Webb measurements are based on relatively small fields of view, which makes the statistics susceptible to cosmic variance, the random fluctuations in galaxy counts from one patch of sky to another. Roman, with its much larger field of view, will reduce the cosmic variance substantially and provide much more reliable statistical measurements of the early galaxy population. The takeaway is that the second major development involves the DESI dark energy program. DESI, the dark energy spectroscopic instrument at Kitt Peak in Arizona, has been measuring galaxy redshifts at unprecedented scale since 2021. The program is currently in the middle of a 5-year observation campaign that will measure redshifts for tens of millions of galaxies, with the data being used to map the cosmic expansion history with extraordinary precision. Quiet pause. The DESI Year 1 results released in 2024 already provided suggestive evidence that dark energy may be slightly time-varying rather than being a true cosmological constant. The subsequent DESI data releases expected over the coming several years will substantially refine this result. If the time variation in dark energy is confirmed, the implications for the cosmological framework and for the cosmic age would be substantial. The combined DESI data, when fully analyzed, will provide some of the most stringent empirical constraints on the cosmological framework ever obtained. The third major development involves the Euclid mission, launched by the European Space Agency in 2023. Euclid is conducting a wide-area survey of the sky in the near-infrared with capabilities complementary to both James Webb and Roman. The Euclid data will provide additional statistical samples of high redshift galaxies and will contribute to the broader empirical picture of the cosmic dawn era. The combination of James Webb, Roman, Euclid, and various other facilities will, by the early 2030s, provide a comprehensive empirical map of the cosmic dawn era at multiple scales. The combined data will substantially advance our understanding of when and how the first galaxies formed, what their properties were, and how they fit into the broader picture of cosmic structure formation. What surfaces from this is that the fourth major development involves the Vera Rubin Observatory in Chile. The Vera Rubin Observatory began full science operations in 2025 and is conducting the Legacy Survey of Space and Time, the most ambitious optical survey ever attempted. The survey will image the entire southern sky every few nights for 10 years, producing a comprehensive time domain map of optical astronomical phenomena. The Vera Rubin data will provide substantial input to the cosmic age question. The Type Ia supernova measurements will substantially improve the precision of the local Hubble constant measurement. The strong gravitational lensing observations will provide independent constraints on the cosmic expansion history. The cosmic microwave background lensing measurements will provide additional constraints on the cosmological framework. The combined effect of these various measurements will substantially advance our understanding of the various open questions. The fifth major development involves the theoretical response. The cosmology community is actively working on refined models that can accommodate the various recent observational tensions. New simulations of galaxy formation are being run with different assumptions about the various physical processes. New analyses of the cosmic microwave background data are being conducted to constrain various alternative cosmological frameworks. The theoretical landscape is evolving rapidly, with substantial expected progress over the coming several years. No one expects, on first thinking about the future of cosmology, that the next decade would offer such substantial expansion of empirical and theoretical capability. No one predicts that multiple major programs would be operating simultaneously on questions that affect the cosmic age. Absolutely no one anticipates the way the contemporary moment in cosmology is positioned to potentially substantially reshape multiple aspects of foundational cosmological understanding. Walk with me through what this implies for the cosmic age question specifically. The various ongoing programs will provide substantial new empirical input over the coming several years. The Roman observations will refine the early galaxy statistics. The DESI program will refine the dark energy constraints. The Euclid mission will provide complementary data. The Vera-Rubin Observatory will provide additional independent constraints. The theoretical work will progressively refine the various alternative frameworks. The combined effect will be a substantial advancement in our understanding of the cosmic age question. There is, in this picture, a particular kind of intellectual optimism that is appropriate to the contemporary situation. The cosmic age question is genuinely open. The empirical work to address it is well funded and well conducted. The theoretical work to address it is active and creative. The next decade will substantially clarify the situation. We are alive at a moment when the cosmic age question is being actively reconsidered, with the work being conducted by the broader cosmology community across multiple specific lines of investigation. Hold this image. The next decade of cosmology will involve substantial new observational programs, substantial new theoretical work, and substantial new computational capabilities. The 5 reasons we have walked through tonight will be tested more carefully than they have been to date. Some of the current uncertainties will probably be resolved. Others may persist for further investigation. The cosmic age value will, by the early 2030s, be substantially better constrained than it is today. What follows from this is that this is part of why the current moment in cosmology is particularly interesting. The combination of the recent empirical tensions, the substantial expansion of observational capability, and the active engagement of large theoretical communities has produced a particularly productive period in the field. The next major advances, whatever they turn out to be, will likely emerge from this combination of ingredients. We are alive at a moment when the cosmic age question is approaching what may turn out to be its most consequential phase of investigation since the original Planck measurements over a decade ago. What this leaves us with is a sense of why the current moment matters. We are alive during one of the more capable phases of cosmological research in its history. The work continues. The instruments improve. The theoretical understanding deepens. The cosmic age question is being investigated from multiple directions simultaneously. The various tensions and alternative frameworks are being progressively tested against the available data. The cosmic age value will continue to be refined, gradually and substantially, through the patient work of the broader scientific community over the next several decades. For the rest of the night, sit with the cosmic age question. The standard value is 13.8 billion years. The value has been the consensus number for approximately 3 decades. It appears in every textbook. It is treated in essentially every popular cosmological discussion as one of the more confidently determined cosmological parameters. The careful work of deriving it from the Planck cosmic microwave background measurements combined with the standard lambda CDM framework is one of the more impressive achievements of modern cosmology. The empirical situation, however, is more complicated than the standard textbook framing suggests. The James Webb observations of high redshift galaxies have revealed structure formation patterns that the standard timeline struggles to accommodate. The Methuselah star age estimates approach or slightly exceed the standard cosmic age. The Hubble tension between local and cosmic microwave background measurements has not been satisfactorily resolved after a decade of careful work. The early supermassive black holes appear too massive for their cosmic ages under standard formation mechanisms. The Gupta cosmological model and various other alternative frameworks have been published with cosmic age values substantially different from the standard estimate. The combined empirical picture is one of genuine open questions about the cosmic age that the standard 13.8 billion year value does not fully convey. The standard value is the best current estimate within the standard framework. The standard framework is the best current theoretical model based on the available data. But the framework is not the only viable possibility, and various empirical tensions suggest that the framework may need refinement in specific ways that could affect the cosmic age value. Picture for a moment what the cosmic situation actually involves. The cosmos has been here for some specific amount of cosmic time. The amount is not arbitrary. The cosmos either is 13.8 billion years old, or 14 billion years old, or 16 billion years old, or 26 billion years old, or some specific other value. The cosmic answer is, in principle, determinable through sufficient empirical and theoretical work. The work has been conducted progressively over the past century, with the precision improving substantially over the past several decades. The current best estimate is the standard value, but the genuine uncertainty in the estimate is larger than the formal precision suggests. Slowly, the camera in your imagination drifts outward. It leaves the room where you are sitting. It rises above the building, above the city, above the planet. It travels outward through the solar system, the galaxy, the local group, the cosmic web of galaxies. It pushes further into the regions of the cosmos that are visible only at high redshifts. The James Webb observations are looking at these regions, returning data that has been substantially reshaping our understanding of the early cosmos. The camera approaches the cosmic microwave background, the diffuse glow that fills the entire observable cosmos. The background represents the moment when the cosmos became transparent to light, approximately 380,000 years after the Big Bang. The measurements of the background have provided the most precise constraints on the cosmic parameters, including the cosmic age. The constraints are precise within the standard framework. They are less precise in the broader theoretical context, where alternative frameworks are possible. The camera continues backward in cosmic time. It approaches the era of inflation, the brief period of accelerated expansion in the very early universe. The detailed physics of inflation is not yet fully understood, with various models producing different specific predictions for the various cosmological parameters. The cosmic age depends on the specific inflationary model, with different models producing different specific values within the broader cosmological framework. The camera turns around and begins the long drift back, through the inflationary era, past the cosmic microwave background, through the cosmic dawn, through the era of progressive structure formation, through the cosmic web development, past the local group, past the galaxy, past the solar system, past the planet, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You are still here. The version of you in this room, on this night, is alive at a moment when the cosmic age question is more open than the standard textbook framing suggests. The standard 13.8 billion year value is the best current estimate. Alternative values ranging from somewhat younger to substantially older are technically possible within various alternative cosmological frameworks. The empirical work to distinguish between the alternatives continues with substantial progress expected over the coming decade. What this means for how you experience the cosmos tonight is subtle. The cosmos around you is the same cosmos that existed yesterday. The cosmic age is some specific value that depends on the actual structure of physical reality. The value is, in principle, determinable through sufficient work. The current best estimate is the standard value. The genuine uncertainty in the estimate is larger than the formal precision suggests. The cosmic story you are part of has a specific cosmic age, but our current best estimate of that cosmic age may need to be revised as the empirical and theoretical work continues. There is something genuinely interesting about being alive during this particular phase of cosmological work. The standard cosmological model has dominated theoretical thinking for approximately 3 decades. The model has been remarkably successful, but the recent observational tensions suggest that some refinements may be needed. The next decade of cosmological work will substantially clarify the situation, with the cosmic age value either being confirmed at the standard 13.8 billion year value or being revised to some specific different value. There is no need to hold all of this in your mind. The 5 reasons will keep their shape, whether you remember the details or not. The cosmic age value, whatever it actually is, will continue to be the cosmic age value regardless of our current best estimate. The empirical work to determine the value will continue. The theoretical work to refine the framework will continue. The various tensions will eventually be resolved one way or another. The cosmos that contains your sleeping body is a cosmos that has been here for some specific amount of cosmic time. The standard estimate is 13.8 billion years. Various lines of recent empirical evidence suggest the actual value may be somewhat older. The work to determine the actual value continues. The cosmic story is, in this sense, still being written in its most fundamental details, with the work being conducted by the broader cosmology community across the coming decades. Sleep can come whenever it wants now. The story has done its work. The cosmic age question is open. The empirical work continues. The next decade will substantially clarify the situation. We are alive at a moment when the cosmic age is being progressively refined, with the work being conducted by the broader scientific community. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.